How are you all doing today?
Morning. Doing well, thank you. How you doing?
Doing good. Anybody have any questions regarding any of the homeworks or the exam or anything?
I got one question on the test.
All right, what's that, Cord?
Problem 3. I was a little bit of trouble thinking about it, but the main thing that's confusing me is it says converting a 4-bit binary number into its equivalent base 10 integer. I just wondered, does the 4-bit binary thing mean anything, or is it just being complicated?
So a 4-bit binary number means that it's got 4 digits. So effectively, what I'm asking you to do is to create a system where you will use 4 voltage sources to generate outputs, 4 voltage sources that are either going to be a 0 volt or a 1 volt. And the idea is that you should be able to generate any signal ranging from 0 to 15 volts.
Okay, awesome. Thank you.
Yeah. So the 4-bit means that you need 4 different possibilities of 0 and 1. So that's where the 4 voltage sources are coming from. Any other questions regarding the exam or anything like that? All right. Well, then today we're going to look at, excuse me, homework. I think it's 10 that I just posted. Give me a that I posted yesterday. Give me a moment to verify that. $223. Okay, so let me share my screen. All right, so the lecture material that I posted for today is on the force response due to sinusoidal inputs. And it is really just a lot of background information on effectively really how difficult it is to solve circuits in the time domain. That's really it. It is leading up to the development of our phasor relationships that we're going to be using. So to that end, I only made a very short homework assignment for this material because it's really, I presented the material more so for you to understand and appreciate being able to use complex numbers than for you to actually have to brute force solve anything using simple time domain techniques because, well, I said simple, but they're not simple. It involves lots of integral differential relationships and just a bunch of ugly calculus, trig identities, and all that kind of good stuff to get even the most basic results for a very simple circuit. So this homework set, I'm asking you to effectively follow along with some of the derivations that I did in the, the lecture. So if we look at homework problem number 1, it asks you all to apply Kirchhoff's current law at the top node of the circuit, develop an integral differential equation for the total current leaving the top node in terms of the common voltage V of t for a specific source voltage that is a sinusoidal function. So let me draw our circuit here. So this is, let me use my black pen. So we have current source, direction up, IS of t, and then let me pop back over here, RLC. That's what I thought. So this is our circuit, and we're told that IS of t has some value. Let's see, Im sine omega t. All right, so if we're going to be applying Kirchhoff's current law at our top node, that means we need to define our currents through our other elements. So I'm going to call this guy direction down IR of t, this guy direction down IL of t, and this guy direction down IC of t. So if I apply Kirchhoff's voltage law, or excuse me, Kirchhoff's current law at the top node, I can see that IS of t is equal to IR of t plus IL of t plus IC of t. So my question to you guys is, how do I turn this Kirchhoff's current law equation into an integral differential equation in terms of V of t?
Can you use the relationship between the current and voltage on a capacitor?
So that will be one thing, sure. So what is that relationship, Cord?
The current through a capacitor is equal to the capacitance times the derivative of the voltage.
Right, and the voltage drop over the capacitor is just V of t. So that took care of that guy. How would we do it for the resistor or the inductor?
The inductor would be the integral of the voltage, right?
It's 1 over L times the integral of the voltage from T naught to T of V of, let's call it X dx, where X is just a dummy variable representing time, plus some initial condition on the capacitor current, or excuse me, inductor current. So that takes care of our inductor. What about our resistor? What relationship would we use there?
Could you just multiply?
I heard, can I just multiply? I don't understand that comment.
Sorry, Sadie, go ahead.
V over R.
Yeah, just Ohm's law, right? Alrighty, so that is all equal to Im sine omega t. So that is part A. You have written a simple differential, or excuse me, integral differential equation. Should be nothing different than what you guys had to do with the general RLC problems. In fact, this one's likely one of the easiest integral differential equations that you've had to write. So for part B, let's check over here. It asks us to take the derivative with respect to time of our results from part A to get a second order differential equation. So let's start with the left-hand side. If I take the derivative of Im sine omega t, what am I going to get?
That would be omega Im cosine omega t.
So the derivative of sine is cosine. I think that's right. All right, let's see. If I take the derivative of c dv by dt with respect to time, what do I get?
C times the second order derivative of vt with respect to time.
If I take the derivative of this guy next, what am I going to have? The resistor current term.
1 over R dv dt.
All right. And if I take the derivative of the inductor current term, what's going to happen?
That's the constant, so it'll go away.
So the constant is going to go away because the derivative of a constant is 0. But what happens when I take the derivative of an integral?
Should just cancel out.
Yeah, so I'm just going to be left with 1 over L t. And so that's my answer for part B. Nothing wild or crazy here. Okay. So if this guy were a DC function, this would be exactly what I was having you all do with the general RLC circuits. This is how it would have looked if you were deriving the relationships for specifically a parallel RLC circuit. But because this guy isn't a DC term, it makes the math going forward to get a solution significantly harder. And we're not going to struggle our way through that ludicrous amount of calculus because we're going to use phasor relationships starting on Monday to negate having to do so much terrible calculus. All right, so let's look. Let me add a page. Let's look at problem 2. This one is a bit more tricky. We are asked to determine the magnitude and phase angle of the voltage V of t in the circuit below as a function of the current magnitude and the values of R and C and omega for an exponential excitation function. So we have current source, IS of t, resistor, capacitor. We are told that IS of t is Im e to the j omega t. So we're working under the assumption that there is no phase angle on our source current, which is really just to make the math easier. And our goal, if I'm not mistaken, is to effectively determine what the exponential response V of t will be for this system. Let me look at the question again. Determine the magnitude and the phase angle of the voltage in the circuit below as a function. Yeah. So we want the magnitude of the voltage and the phase angle of the voltage. So that means we're going to look for a magnitude portion and a phase angle portion. So yeah, we're effectively looking on how to get a complex response. All right. So based on what we did on our previous problem, how would we develop a differential equation relationship for this system?
Go ahead and do KCL again.
Yeah, KCL again, right? So we can start with IS of t will be equal to, I'm not even going to bother writing down IR of t and IC of t because we can get there pretty easily. So what's the current flowing down through the resistor expressed in terms of V of t?
V of t over R.
So let's call it 1 over R, just to be clear here. 1 over R V of t. And what is our current flowing down through our capacitor going to be?
C dVt over dt.
All right, so if we have an exponential excitation function, it should not be a large leap of the imagination to assume that our response will also be an exponential function. However, I am going to include the possibility that the phase angle of our response will not match the phase angle of our source. So that's where that theta v is coming from. So I'm saying that effectively, I can't just apply Ohm's law here, and we've seen that because we have a derivative-based relationship. So is everybody okay with this waveform being a guess value of how our response should look?
Yep.
Yes, sir.
Okay, so under that constraint, we can substitute in our values for IS of t and our guess value for V of t. And so we will have Im e to the j omega t is equal to 1 over R times Vm e to the j omega t plus theta v plus c times the derivative. So what's the derivative of V of t with respect to time?
That would be omega Vm e to the j omega t plus theta v.
So you said omega Vm e to the j omega t, but there is a factor of j that's also multiplied by t. So shouldn't it be j omega Vm e to the j omega t plus theta v?
Yes, sir, my bad.
So j omega, then we have our c factor, Vm e to the j omega t plus theta v. Alrighty, so the next thing that I'm going to do is I'm going to slightly re-express my exponential functions. So I can say that e to the j omega t plus theta v is the same as e to the j omega t multiplied by e to the j theta v. Is everyone okay with that operation, or do you need an explanation?
Looks good.
Yeah, so when I multiply those two exponential functions together, I can simply add their arguments. I can do the same for my second term, plus j omega c Vm e to the j omega t e to the j theta v, and all of this will be equal again to Im e to the j omega t. So I can see that I have a common factor of e to the j omega t in all of the terms, so I can divide both sides by that, and I'm left with Im is equal to 1 over r Vm e to the j theta v plus j omega c Vm e to the j theta v. I can group like terms and find that I will have 1 over r plus j omega c multiplied by Vm e to the j theta v. And finally, can rearrange slightly and see that Vm e to the j theta v is equal to Im divided by 1 over r plus j omega c. So what I have done here is I have a complex number on the left-hand side because it has some magnitude and some phase angle, complex number. And on the right-hand side, I have a rectangular form complex number. And so what I want to do is figure out what the magnitude of the right-hand side is, because the magnitude of the complex number on the right-hand side has to equal the magnitude of the complex number on the left-hand side. And similarly, the phase angle of the complex number on the right-hand side has to be equal to the phase angle of the complex number on the left-hand side. So I'm going to need to convert, well, not necessarily convert the right-hand side complex number, this guy, into a polar form, but I need to convert it into a form to where I can easily determine what its magnitude and phase angle are. Do I have any suggestions on how to go about doing that? So let me rephrase my question. I have a real number in the numerator and a complex number in the denominator. How am I going to get rid of the complex number in my denominator?
Could you use the conjugate?
Yes. So I'm going to multiply this guy by the complex conjugate of the denominator. So that would be 1 over r minus j omega c and I'm going to multiply the numerator by that same amount. So I'm multiplying by 1, but just in a weird way. So what's going to happen to my denominator here?
It'll become 1 over r squared plus omega c squared.
Exactly right. My numerator becomes Im divided by r minus j omega c Im, which I can put this in a rectangular form now that's a little more obvious. So I will have, make sure I distributed the Im correctly. Yeah, so this is going to look like minus so now that I have my right-hand side in a more explicit rectangular form, how would I determine the magnitude of this complex number?
You square both of them, add them up to take square root.
Yeah, so that's exactly right. To determine the magnitude of a complex number, I can square the real part, square the imaginary part, add them together, and take the square root. So that means the magnitude of Vm, or no, not the magnitude of Vm, Vm, because that is inherently the magnitude, is going to be the square root of Im over r divided by 1 over r squared plus omega c squared, this whole thing squared, plus this whole thing squared. Technically, this should be negative omega c Im, but when we square it, it really won't matter. So let's see what's going to happen with this guy. So we're going to have the square root of Im squared times 1 over r squared plus omega c squared divided by 1 over r squared plus omega c squared quantity squared. Is everybody okay with that mathematical operation?
Yes, sir.
So I can cancel out this guy and lower the power there, and I find that my magnitude is then Im divided by the square root of 1 over r squared plus omega c squared. So I've expressed my magnitude in terms of Im, r, omega, and c, just like I was asked to do. So looking back at this guy, how am I going to get my phase angle theta v? Can anybody remember the complex number relationships for determining phase angle when we have a rectangular complex number?
It was the inverse tangent of the complex part over the real part.
That is exactly correct. So theta v will be the inverse tangent of, I might need more room here, the imaginary part. So that's going to be negative omega c Im over 1 over r squared plus omega c squared divided by the real part, which was Im over r 1 over r squared plus omega c squared. So we can see that those common denominators are going to cancel each other out. Additionally, there's a common factor of Im in both the numerator and the denominator. Yeah. So we're going to have the inverse tangent of negative. So we have omega c 1 over r. What's this going to simplify to?
Omega CR.
Yeah, so negative omega RC, and we can use a simple identity. So the inverse tangent of a negative number is the same as the negative inverse tangent. So that would be negative inverse tangent omega RC. You don't necessarily need to use that one. This guy is perfectly sufficient, but I prefer to not have negative signs inside my argument. All right, so that was problem 2 the whole thing. We figured out what the magnitude is, and we figured out what the phase angle is. So if you've watched the video lecture, I did the exact same thing in both the time domain and then what I like to call the mixed domain, which is what we just did this guy here in, for a simple RL circuit. And we observed that this math wasn't crazy difficult by any stretch of the imagination, but using the sinusoidal functions and all the trig identities, it gets super ugly, super duper quick. So what we are going to cover for next Monday is phasor domain relationships. And I'll talk about phasor domains, the phasor domain real quick. So let me add another sheet here. So in the time domain, we're dealing with voltage signals of the form Vm sine or cosine omega t plus some phase angle theta v. And these time domain signals are characterized by their magnitude, their angular frequency, and their phase angle. In the video lecture, I explain how and why we could go to what I'm going to call the mixed domain, where we could see that V of t above is simply the real part of a complex representation, Vm e to the j omega t plus theta v. So this guy is our mixed domain representation of that source, of that voltage in question here. And the reason this works is the superposition principle, effectively. Euler's identity, e to the j omega t, can be written as cosine omega t plus j sine omega t. So if we have some cosine excitation function, and we know how our circuit is supposed to behave, we can then add on an imaginary sinusoidal excitation to make our signal behave as if it were an exponential excitation, where the real part of the exponential response is due to the real part of the exponential excitation, and the imaginary part of the exponential response is due to the imaginary part of the excitation. So because this complex number is defined by the same magnitude, angle, frequency and phase angle, we can actually flip back and forth between these two forms with an extraordinary amount of ease, and this is the relationship that relates them. The phasor domain, which is what we're going to be using, is just an engineering shorthand notation. So the phasor domain has what's called a suppressed frequency. So we are leaving the time domain entirely. All we are doing is dividing our mixed domain signals by a factor of e to the j omega t, and it leaves us with just our magnitude and a phase angle. So these are all three different ways to represent the same signals, but these relationships right here, these phasor domain relationships, are going to wind up actually having the least amount of math. So it's going to be the easiest way to perform our circuit analysis. So I'll leave it to you guys to watch the video lecture that gives a more detailed explanation of where the phasor domain relationships and all that kind of good stuff come from. And then we'll talk on Monday, unless anybody else has any questions. All right, you guys have a good 4th of July weekend. Don't do anything too dangerous. Blow off any fingers or appendages with fireworks and alcohol. You know, just have a good time.
Sounds good. You do the same, sir.
All righty, catch you guys later.